I actually really enjoyed that talk by Anna. Thank you. We had quite a fun week a week ago or so in Bern, figuring out what the seismicity of Venus might be, and agreed that breaking news: Mars is not dead, just a bit of an old doddery man. Venus is very much young and alive. And I'm not going to give you figures for what we think the earthquakes are going to be, because we're still working that through. But it's going to be on the order of hundreds, probably, of magnitude fives. So it would be great one day to go there with a seismometer and look at Venus quakes. But one of the reasons that, just to give you a bit of background really to Venus and why it's interesting, is that if we compare the terrestrial planets, you'll see very much that Venus and Earth are a pair on their own. They're colossal compared to the other planets. I think Mars is very much intermediate, and who knows where the boundary is between, a Moon, Mercury-like planet and a Venus, Earth-like planet. But I think we do have a lot to learn from Mars. But we have an awful lot more to learn from Venus. I'll just get that in there. And I think it's very much an active planet with active geology. I think we can see that in the other aspect of these maps. So not just the area, the scale of the planets, but the topography. We tend to think of, Earth and Venus as being rough planets. But in comparison to the smaller planets, they're not at all. And the topographic extremes on the Moon, Mercury, and Mars are much greater. Now, Mars has remade a lot of its surface, but Mercury and the Moon, largely that topography comes from impact craters. And on all three of those planets, the surfaces are ancient, or mostly ancient. Whereas Earth and Venus have relatively flat surfaces. There are differences to do with differences in density and composition and tectonic activity and volcanic activity, but the extremes are much less. And they both have the characteristics of having remade their surfaces recently. I mean, we know from impact cratering that Venus's surface is less than about 1 billion years old. It's also geologically complex. It has a global network of rifts where are we there? In purple, shown here. And these strange circular features are coronae, which are probably intrusive features associated with rifting and volcanism. Lots of these big red patches, which are large volcanoes ranging down to small volcanoes. And all these areas in blue are compressional features. So interestingly, we have a network of rifts on ridges parallel to the spreading ridges on Earth, covering pretty much the same sort of distances, but we don't have a corresponding network of subduction, and we don't see the kind of morphology that goes with oceanic plate tectonics. We do see the ridge features. So we see this sort of half space cooling pattern to the topography on Venus in the same way as we do on the oceans of the Earth. But when we look at those rift systems, we can see they sit on a ridge, but they look very, very different. And we know from the impact craters, and we know from looking at the geology around them, that what's either side of them is not parallel new oceanic crust going to older surfaces. So this is a very different kind of rift system. And maybe it may be related to mantle convection processes. It may be related to the kinds of magmatism, but most likely it's related to the buoyancy of the upper crust and lithosphere on Venus because of the high surface temperature. The surface temperature on Venus is about 450 degrees C. I'll just go back a moment. I haven't pointed out these green areas, which are continental-like tesserae regions. And I'm going to actually focus on a region down here, coming down from Alpha down to Lada, Terra, in this region here, rather than these global rift systems, because I think they tell us something about how big planets like Earth and Venus work, and how there's more than one mode of behavior. So coming forwards, I think many people have suggested that Venus may be somehow similar to an Archean Earth, a planet in which more than 2.5 billion years ago, the heat flow was so high on the Earth that it was unable to lose all of its internal heat. And in that situation, we will have had something maybe akin to plate tectonics taking place, but not in a modern sense. In other words, not with a subduction-driven process, but perhaps still with new oceanic crust being made in spreading centers and so on, and certainly with proto-continents, which are shown here, what are now the Archean cratons. And one possibility is that these cratons and the oceanic part, if you like, took part in upper mantle convection, and that the lower mantle was isolated. And every so often, as the lower mantle heated up, it becomes unstable and overturns, and we get a regional overturn event, something that I've heard called an overturn upwelling zone, or an OUZO, but mantle overturn is a very common phrase for this. And during that event, we bring up primitive mantle from the lower mantle. We generate extensive melting, a large number of localized plumes. We rework all of that crustal material, both the continental and the oceanic crust. And actually, we maybe stabilize some of that into cratons. But it's not a global event, which was something we thought for a while about Venus. And this maybe corresponds with episodes on the Earth of increased magmatism and continental crustal growth production. The last such event, possibly on the Earth, might be what we call the Cretaceous Superplume, or the breakup of Pangaea. I'm sure it actually extends well beyond the Cretaceous. But about 200 million years ago, the Earth looked like this: Pangaea as a single sort of, well, more or less single landmass. And whether that insulated the interior and allowed that part of the mantle to heat up, while the outer part, the Panthalassa in this case, was able to remain cold, or whether it's the accumulation of subducted oceanic crust underneath this supercontinent. Whatever the reasons, this supercontinent was unstable and broke apart. And we can see that in two things. We can obviously see it geologically in the presence of large igneous provinces. And in this case, I've just shown the proto-Atlantic rifts, but you could do the same thing for the Indian Ocean and elsewhere. We can also see it in the geoid. There's a geoid high currently out in the Pacific, and although these may have moved slightly, they take about 100 million years to decay, these geoid highs and lows, so they reflect in some way what was going on during the breakup of Pangaea. And there is a low under the Indian Ocean, which is part of the reason that kind of India raced northwards towards Asia. But there's this broad, big high underneath what will become the Atlantic as that opened up. And these plumes, or large igneous provinces, were generated probably by that upwelling mantle underneath. And these sorts of features are what I think we can refer to as the superplume, or the regional overturn, or the OUZO event. And we see something similar on Venus for reasons I won't go into, but those spreading ridge-like rift systems are probably similar to our spreading rift systems, although in a more static way. They're not generating spreading centers. And therefore, we can sort of think of this as oceanic crust, or more oceanic-like crust, basaltic crust on the surface of Venus. Whereas concentrated onto this hemisphere are all the highland areas, which we think are, well, certainly not basaltic, let me put it that way. They may not be granitic, there may be some other composition, but not a basaltic composition. And they appear to stand high from an isostatic perspective, so that they are different in density, they're lower in density. And we also see in the geoid topography ratio a high Under Iceland in the north here, which is a well-developed plume and corona system with some rifting, and under Lada Terra here, which is what I'm going to focus on shortly. Whereas under Atla, at the convergence of some of these rift systems, we see something much more like the Hawaii plume. So we see large volcanoes. This volcano here, Mat Mons, is almost exactly the same size and nearly the same shape as Mat Mons. And colleagues of mine at Imperial have done some detailed mapping to show the development of that hotspot and plume over probably a 60 to 100 million year time period or thereabouts, from initial sort of flood basalts through to a well-developed plume system. But again, one that is not going anywhere because the lithosphere is not moving very far across the planet. It is moving, it is mobile, but over maybe tens or hundreds of kilometers, and it's sort of like a pack ice. It's jostling around more or less where it is. Focusing on Lada Terra, this is an unusual highland. Terra means highland, or earth, I suppose, but highland area. We only have one distinct area of tesserae up in the north, which is Alpha, which is incidentally where Da Vinci is going to land. If it survives its landing, it will give us some information from there. But we see patches of tesserae and broken up and in different places across Lada Terra. And we also see major rift systems and these corona features across that surface area.
That's 11 minutes.
Great, thank you. And next to it is one of the largest corona on Venus, this highland area called Quetzalcoatl. And also we have just off to the north here, we have some massive lava flows you can just see in the edge of this image here, which are very similar to the Mullen Sky kind of volcanoes related to the Atlantic opening. So we sort of think that these areas are probably, and the corona are probably large igneous provinces or equivalents of them. My student, Connor Hode, has mapped this area in great detail and given us some insight and parallels to that opening of the Atlantic and what it might look like on Venus. So I'm just going to take you round to look at some of these features. Otogen, let me point them out first. Otogen on the right here, there's two sort of main rift arms here, and Eithinoha and Lamo and Sarpanitum, we're going to talk about both of those rift arms and the corona on them, and then I'll focus on this Cocomama area of tesserae shortly. So Otogen is a sort of classic corona. It has a high in the middle and a trough around the outside, which is tectonized. It sits within the rift system, but clearly deflects the rift system and is somehow connected to it. I kind of view this as a very large sill-like feature. Others view this as a large igneous province. I think it's all part of the same package. We can see a great many small volcanoes associated with it. So as I say, I imagine a sort of ponded sill below the crust, that evolving and feeding all those small volcanoes. That ponded sill gives you the topographic signature, the trough around the outside and the high in the middle. And as it cools, that middle will subside, and we see that evolutionary model in other coronae. Whereas around into the tesserae where they're concentrated in Lamo tesserae here, we see a feature that to me looks a lot more like something like Yellowstone, a caldera-like corona, perhaps with a magma chamber underneath it, but no great evidence of volcanism. There's a few small cones and things like that. Perhaps this is going to erupt in a big way at some point, who knows? But something that there seems to be a relationship between crustal type, whether we are coming into the basaltic plains or whether we're here coming into a more continental-like tesserae region. Looking at that in detail, and we can see how the corona is interacting with the tesserae fabric around it. So we can see some of those fractures propagating out, and these are probably dike systems extending out into the tesserae. Eithinoha is a really interesting corona because it looks like it was once more like Otogen, but has since perhaps stopped evolving and has been ruptured through by the ongoing rift system. And this relates to something that we see in Parga and Hecate rifts elsewhere on Venus, where the relationship between coronae and rifting is really dynamic. There isn't one comes first. And this maybe has something to do with the ongoing argument on Earth as to, do large igneous provinces drive rifting and ocean formation, or does plate tectonics and ocean formation drive large igneous provinces? What we're seeing on Venus is that those two things go hand in hand, and they are interactive. It's not one or the other, it's both. And so I sort of finally want to get on to Cocomama tesserae, because I think we see a really interesting story here about what's going on with this rift system and what may be going on in Lada Terra. So we see a pattern of tesserae, various blocks here. And at first we thought, well, these plains are being flooded by lavas coming, in this case, from Eithinoha. And they're ponding in this area here. Well, that is true, but this low-lying area here was once part of the tesserae. So it was part and parcel of the tesserae package. And so now we're starting to come to the view that the tesserae have a core region, which is equivalent to our Archean cratons, I suppose. And then they accrete material onto them. And some of that accreted material, like here, is continental, and some of that accreted material is plains. And sometimes those plains get highly deformed and broken up, but in this case, it just appears that this plains unit abutted against the tesserae, and we can see a really sharp contact between that plains unit and the tesserae. But we can see that that plains unit is old. It is cut by fractures that are also in the tesserae that don't cut the much younger flows coming from the coronae in the rift system at present. So we think these are really quite two distinct ages. Unfortunately, we can't date any of these things because of the way dating works on Venus. We only have 1,000 craters, and the resolution isn't such that we can date these surfaces except to say that they're less than 1 billion years old. But this also seems to tie with that accreted margin sort of model, if you like. And on the other side, we can see that, again, this more continental-like tesserae was accreted onto that plains unit. Almost a picture of Greece, if you like. Ocean continent slithers piling in, not perhaps traveling very far, but far enough to give you a collisional event and an accretion of material. Beyond that, we have the rift system developing, and a lot of associated volcanism with that rift system cutting through the tesserae region. And we have what we think is a developing corona in this area here. It's not clearly a corona yet, but there appears to be magmatism coming in, and perhaps another plume system in place. Okay, that's I think that's gone out of order, but that's a close-up of those graben coming across into the plains unit, giving you that edge feature there. Sorry, that should have been earlier. So what does this say about rifting on Venus? Well, we think this might be a Cretaceous Superplume, an OUZO event, some kind of large-scale process in the mantle, from a sort of maybe two-layer convection type of process. We think fundamentally what it may be telling us is that large terrestrial planets, and we maybe see the beginnings of this on Mars, are bipolar in their convection systems, and they generate an almost continental hemisphere and an almost oceanic hemisphere, if you like. On Earth, that gets moved around considerably by plate tectonics today, but in the past, perhaps Earth looked a lot more like Venus when it was when the heat flow was higher and it was unable to subduct in the same way as today. And so we see, I think, two regimes on Venus. But what's really interesting about this area is if we look at the corona, we can work by Anna Gulcher has shown that we can classify corona from their morphology into active and inactive coronae. And most of the corona that I've shown you appear to be active. In fact, most of the active coronae appear to be in the Lada Terra area and in Parga Chasma, which runs up through here. There are a spattering of others across the planet. So there's clearly magmatism elsewhere on Venus. But the fact that these coronae in the plains, in the rift system here, look more like classical coronae, whereas these coronae in here with the tesserae appear more like large igneous provinces and multiple stages of intrusion and rift development and so on, seems to suggest that we have something more like the large igneous provinces on Earth in the breakup of Pangaea, compared with what are properly spreading ridges on the Earth, but again, continuous magma systems underneath. If this was East Pacific Rise, this would be a continuous magma system rather than coronae, but something that's clearly parallel. And as I say, if we look in at the corona, we can see evidence for activity. If we look in Venus Express data, now these data have to be taken with a great pinch of salt, because there are no atmospheric filters, and we have to play around with a lot of corrections, and the topography is pretty poor here and so on. But there do appear to be patterns of low emissivity which suggest, or which parallel the non-basaltic crustal regions. So the tesserae regions here show up in blue and purple. But some of the coronae show up in the reds, the higher emissivities, which are indicative of younger, fresher surfaces, perhaps even volcanic activity at the present day. So it would be really exciting to go there and look at this area and think, do we have actually an active, ongoing overturn type of process on Venus that would tell us a lot about how big planets work, would tell us a lot about what went on in the breakup of Pangaea and the rift systems as they opened up, and the large igneous provinces as they opened up. We may even see an active large igneous province or two on the surface of Venus. So we could learn a lot from Venus and Earth, from the history on the Earth and from the observations on Venus, by going there forwards in time. And I'll leave that summary up for you to dwell on and ask questions. Thanks.
Brilliant. Thanks, Richard. So we're over time, but we'll take questions anyway, since it's the last talk. Any questions? I've got a question. So I got the feeling that magmatism is quite common on Venus. I mean, can you give some sort of feeling for, I don't know, the relative importance of faulting and dike intrusion in this extension?
That's a really interesting question, because I'm sure diking is important, and we see a lot of graben that we think probably are related to dike intrusions. But Venus is actually probably one of the most fractured planets there is. So there are tectonic fractures everywhere, as well as probably igneous fractures. And it's not always easy to tell them apart. If I try and go, yeah, that'll do. If I go backwards one, all these rift systems will have tectonic fractures within them and dikes within them. And telling one apart from the other just from a surface imagery is pretty tricky. You could argue that every graben is a dike. You could argue that every graben is a tectonic graben, but it's, where that line is drawn is quite hard to say. My guess is that in those active rift systems, it may be as much as 50-50, but certainly I would say that the dominant topography is tectonic, and we see certainly half graben and things like that are tectonic, but there are dike swarms everywhere on Venus, almost certainly.